This is session D5, 2 spin 1/2 particles. Last lecture, D4, we covered spin 1 and other spin values, and also photon polarization. Previously, we've covered spin 1/2 particles, but as a single particle. Today we'll explore 2 spin 1/2 particles. To get there, we'll first define tensor product states and explore addition of angular momentum. Here's our roadmap. We'll do tensor product states, pure states and entangled states, operators on tensor product vector spaces, addition of spin angular momentum, identical indistinguishable particles, Pauli exclusion principle, 2 electrons in the same orbital, oxygen molecule, triplet oxygen, electron and proton spins in hydrogen atom, hyperfine splitting, proton spins in hydrogen molecules, proton and neutron spins in the deuterium nucleus. Then we'll recap that and we'll do a brief material on nuclear magnetic resonance and magnetic resonance imaging. Tensor product states. So far we've only dealt with single particles. In the C series of lectures we dealt with a particle's spatial state. In the D series of lectures we dealt with a particle's intrinsic spin angular momentum component in some direction, spin state, which was a separate independent state space than the state space for spatial states. Now we deal with 2 separate independent state spaces, state space 1 and state space 2. For any particular problem, we identify each state space and we do not change the indexing 1 and 2. For one problem, state space 1 could be the spatial state for a particular electron in an atom, and state space 2 might be that electron's spin state. These are independent degrees of freedom for the particle, separate state spaces. For a different problem with 2 particles, state space 1 could be the spin state for particle 1, and state space 2 could be the spin state for particle 2. For simplicity and clarity, this lecture will always use 2 particle spin states, not 1 spatial state and 1 spin state. This approach can readily be extended to more than 2 state spaces, but we will only consider 2 state spaces. This is a possible time to take a break. Let ket W be the system combined quantum state of 2 particles' spin states, where particle 1's spin state is ket U1 and particle 2's spin state is ket V2. These are separate independent state spaces. Initially, we will use the subscripts 1 and 2 to tell us which particle the single particle state refers to. We define the tensor product notation for state ket W as follows. Ket W equals ket U sub 1, tensor product ket V sub 2. This means that system state ket W equals state ket U for particle 1, tensor product with state ket V for particle 2. Tensor product has specific mathematical properties, but we can usually think of the meaning as simply being and. System state ket W equals state ket U for particle 1 and state ket V for particle 2. Ket U sub 1 is a spin state vector in state space capital U of particle 1. Ket V2 is a spin state vector in state space capital V of particle 2. Capital U and capital V are separate independent state spaces. Ket W equals ket U for particle 1, tensor product ket V for particle 2, is a system state vector in the tensor product vector space capital W equals capital U tensor product capital V. Tensor product is an extension of direct product, but we're not going to cover the distinction. Tensor product is not inner product and it is not outer product. Tensor product is not the vector cross product. If I say cross at some time, I mean in tensor product in this lecture. Hopefully I won't do that, but if I do, bear with me. Cross means tensor product. Tensor product is linear, distributive, and associative. If we have a ket, alpha ket S for particle 1 plus beta ket T for particle 1, tensor product with ket V for particle 2, that is the same as alpha times ket S for particle 1 tensor product ket V for particle 2 plus beta ket T for particle 1 tensor product ket V for particle 2. And similarly, if we have a linear combination for particle 2. Tensor product is not commutative, and we will never change the ordering of the terms for particle 1 and 2. As long as we maintain the tensor product term ordering 1, 2, we often drop the subscripts, but we must remember that the first term of each tensor product is for particle 1, and the second term of each tensor product is for particle 2. If there's ever any doubt, put in the subscripts. So we will generally write that ket W for the system equals ket U tensor product ket V, and we will know and remember that ket U is for the first particle and ket V is for the second particle. We will remember that without expressly putting in the subscripts. For spin states, we can use the label in the ket to tell us the spin state of the particle. For example, we could have a system that of two particles that was in two spin 1/2 particles that was where the first particle was in spin state Z plus or Z up, and the second particle was in state X minus or X down. This is a possible time to take a break. For many problems with two spin 1/2 particles, we'll choose a single direction in space, typically plus Z, for measuring the spin component of both particles. We don't have to do this, but often it will be convenient to do this. In this case, we can use two simplifications of notation. If we're implicitly using the Z direction for our measurements of spin, then instead of writing Z semicolon plus, we can just write up arrow. We could write plus, but I'm going to use up arrow. And instead of writing Z semicolon minus, I will write down arrow. So here we have a system of two spin 1/2 particles, and the system state is that particle 1 is in Z up, Z plus, and that's tensor product with particle 2 being in state Z down or Z minus. For two particles, we can also simplify this by putting both states in one ket. This is just a shorthand. It's always a shorthand for the tensor product. So we will have a ket with two up arrows, and that means that the first particle is in spin state up arrow, or Z plus, and the second particle is in state up arrow, or Z plus. So it's just a shorthand for this tensor product. Likewise, a ket with an up arrow then a down arrow means that particle 1 is in the up state, Z up, and particle 2 is in the down state, or Z down, or Z minus. So we will have all four of these cases for two spin 1/2 particles. Up, 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 down, up, down. Notation such as up arrow in the ket does not show the tensor product symbol explicitly, but this is a shorthand of notation. This is a tensor product when we show the full notation, and we must remember that it is a tensor product, and we must preserve the order of terms. Under no circumstances can we reverse the order of the up and down arrows within the ket. I don't want to use the notation ket plus for Z plus of a single particle in this lecture, because ket plus and ket minus have different special meanings for combined system states of two spin 1/2 particles in modern quantum technologies. And I don't want to confuse you with that, so I'm not going to use that as a single particle spin state. You may also see notations such as ket 00, ket 01. We won't use that in this lecture. There's nothing wrong with that notation. Generally, these will use some definite mapping, such as 0 being the same as Z plus and 1 being the same as Z minus. Nothing wrong with that notation. We're just going to stick with the up arrows and down arrows. Now for two photons, which are spin 1, not spin 1/2, this lecture does not apply. See the next lecture, D6, which will talk more about polarization states than spin states. This is a possible time to take a break. Now, every ket form has its dual bra form, with the first term of the tensor product being the bra for particle 1 and the second term the bra for particle 2. So bra W is bra U for particle 1, tensor product bra V for particle 2. If we need to use that notation in this lecture, I'm going to put the subscripts after the vertical bar, but other authors may put the subscript before the left angle bracket. So you may find 1 bra U tensor product 2 bra V, and that's fine. Different authors might put the index subscripts for the bras before the left angle brackets or after the vertical bars. The subscript will always be after the vertical bar for kets. So here are some tensor product bras. Bra U tensor product bra V. Bra Z plus tensor product bra X minus. And again, we can shorten the notation. We can have bra up tensor product bra down. And we can put both arrows in the same as one combined label inside the bra. We can have bra for up arrow, bra for up down, bra for down up, and bra for down down. The bra form for tensor product is also linear, distributive, and associative, as you would expect. Now, we need to identify the inner product between two tensor product states. So the inner product between some tensor product bra and some tensor product ket. So for the system, let ket P represent the state ket Q for particle 1, tensor product ket R for particle 2, and ket S be ket T for particle 1, tensor product ket U for particle 2. And obviously the bra form for P is bra Q tensor product bra R. No problem there. Now, the inner product of bra P with ket S is defined to be the inner product of bra Q with ket T for particle 1 times the inner product bra R with ket U for particle 2. That is the definition of the inner product. It's a complex number. I mean, each of these single particle inner products was a complex number. So this is one complex number, this is another complex number. We're multiplying them together. The product of two complex numbers is a complex number. So the inner product between, for tensor state, bra P with ket S is a complex number. This is a possible time to take a break. Pure states and entangled states. The tensor product vector space, capital W equals capital U tensor product capital V, is the vector space whose elements are complex linear combinations of elements of the form U tensor product V, or ket U tensor product ket V. Different notation, same thing. With U being an element of capital U and little v being an element of capital V. A pure state can be written as ket U for particle 1, tensor product ket V for particle 2, for some U and V in the space. An entangled state is a linear combination or superposition that cannot be written in that simple tensor product term form. All states in the first section of this lecture were pure states. But entangled states are common in atoms and molecules and are important to modern quantum technologies. For two spin 1/2 spin states measured in the plus z direction, plus z basis, we could choose the following four pure state vectors as an orthonormal basis for the tensor product vector space, and we'll use the shorthand that we previously discussed. So our four orthonormal basis vectors will be up up, up down, down up, and down down. You can and should verify that these are orthonormal with the inner product definition that we had in the last section. Now, linear combinations of these basis vectors are also vectors in the vector space. Following are four important examples of entangled states for two spin 1/2 spin states, measured in the plus z direction or basis, using our previous shorthand. So the first ket is capital Phi plus, and it's defined as 1 over square root of 2 times the sum of up up and down down. This tensor product state will sometimes be called just ket plus by some other authors. We're not going to use that distinction, but this is why I didn't want to use ket plus as a single particle state, because it often is used as the special name for this tensor product entangled state for two spin 1/2 particles. Now the tensor product state capital phi minus is defined as 1 over square root of 2 up up minus down down. State ket psi plus is defined as 1 over square root of 2 up down plus down up, and state capital psi minus is defined as 1 over square root of 2 up down minus down up. These four states are called the Bell basis for the tensor product vector space of two spin 1/2 particles, spin states. These are each entangled states. They cannot be expressed as a pure state, as a single tensor product term. This is true regardless of the basis we choose, which we will not prove. Each of these states is normalized, which you can and should verify. Each state is orthogonal to the other three, which you can and should verify. These four entangled states form an orthonormal basis for the tensor product vector space of two spin 1/2 particles, spin states. This is a different basis than the four orthonormal pure states. So the same vector space, different basis. That's fine. You can verify that each of these four pure states can be expressed as a definite linear combination of the entangled Bell state, Bell basis states. Each of these entangled states is maximally entangled, though we will not define this nor use it in this lecture. Entangled states are an important feature of quantum mechanics, and this was recognized early by Schrödinger, Einstein, Bohr, and others. This is a possible time to take a break. Here are some other entangled states. If you look at these, I think you can convince yourself that they cannot be expressed as pure states. 1 over square root of 3 up up plus square root of 2 over square root of 3 down down. 1 over square root of 3 up up plus 1 over square root of 3 down down plus 1 over square root of 3 up down. 1 over square root of 2 z plus tensor product x minus plus z minus tensor product x plus. None of these can be expressed as a pure state. Now, let tensor product state W be alpha tensor product of U for particle 1 with V for particle 2 plus beta tensor product of S state S for particle 1 and state T for particle 2. Now I'm not showing the tensor product symbols here, and if I didn't introduce this shorthand earlier, I should have. So as long as we maintain particle 1 before particle 2, we can choose to omit the tensor product symbol as long and leave it be implicit as long as we are careful with what we're doing. So this state alpha UV plus beta ST, it is entangled if neither alpha nor beta are zero, none of these states are the zero state in its vector space, states U1 and S1 are not multiples of one another. The states are independent, and states V2 and T2 are not multiples of one another. The states are independent of one another. If all four of those things are true, then this state is entangled. Is the following state entangled or pure? 1 over square root of 3 up plus square root of 2 over square root of 3 down up. Now, you might be inclined to say, well, it's entangled because you wrote it as two terms, so it must be two terms. But that's not true. Pause the lecture and see if you can figure this out. That is a pure state. Let's rewrite this and see why it's a pure state. So here we're starting out with the state, and we'll write it more explicitly. So we're going to take this up and turn it into up 1, up 2, and take this down up and replace it with down 1, up 2. And then we see that both of these terms, although they're written as two terms, the state for particle 2 is the same. It is up 2. So we could combine the expressions for particle 1 into a single state, 1 over square root of 3 up 1 plus square root of 2 over square root of 3 down 1, in parentheses. That state involves only particle 1, not particle 2, and we tensor product that with up 2. So it is the product, a single term product, tensor product, of a spin state for particle 1 and a spin state for particle 2. So it is a pure state. Is the following state entangled or pure? 1/2 up minus up down plus down up minus down down. Pause the lecture and see if you can figure this out. So here's what we started with. Let's re-express that in terms of states for particle 1 and states for particle 2. So instead of up in one ket, we're going to say ket up, where the first one is for particle 1, the second is for particle 2. We write that all out. We can put in the subscript indices just to make sure we don't mess up. It turns out that of the 4 terms inside the parentheses, the first 2 have the same state for particle 1, up 1. So we can re-express that as up 1, and then a state for particle 2, which is up minus down. And the third and fourth terms, they share the same state for particle 1, down 1, down 1. So we can rewrite that as down 1 times parentheses, up 2 minus down 2. And now we notice that the state for particle 2 is identical between these two. It is up minus down, and so we can combine the state for particle 1. So we have 1/2 parentheses, and then another set of parentheses, up 1 plus down 1. That came from here, up 1 and down 1. Tensor product with up 2 minus down 2. And if we write that out with the tensor product symbol, and we take this 1/2 and we turn it into 2 1 over square root of 2's, we find that this is the spin state for particle 1, and it is actually normalized. This is the spin state for particle 2, and it is normalized. We have the tensor, one single term, tensor product of a spin 1 term, a particle 1 term, and a particle 2 term. So it is a pure state, and in fact, this is the same as x plus, and this is the same as x minus. This is a possible time to take a break. Operators on tensor product vector spaces. We have the tensor product vector space for two separate independent state vector spaces. Now we need operators on that tensor product vector space. Let F1 be an operator on states on the first vector space, for example, particle 1's spin state. And let G2, G sub 2, be an operator on states on the second vector space, for example, particle 2's spin state space. Then define the tensor operator F1 tensor G2. When this operates on state U1 tensor V2, this is defined as operator F1 operating on ket U1, tensor product with operator G2 operating on ket V2. F1 is an operator operating on U1. It is going to produce a new ket in particle 1's spin space, spin state space. Operator G2 operating on ket V2 is going to produce a new ket in particle 2's spin state space. So we will end up with a particle 1 spin state tensor product with a particle 2 spin state, just as we've said before. Now these are operators, but I'm not going to use the caret above these operators. I'm not going to write it as f caret sub 1 in this lecture, because we're going to need some real spatial vectors, and I'm going to reserve the caret for real spatial unit vectors. So these operators for spin states, they're operators, but they're also matrices, matrix operators. I'm not going to use the caret for them, so that I can reserve the caret for real space, spatial unit vectors. Now, some operators sum the effect of acting on each space separately. If there's no interactions between the two particles, the system Hamiltonian operator H is Hamiltonian H1 for particle 1, tensor product with the identity operator for particle 2, plus the identity operator for particle 1, tensor product with the Hamiltonian for particle 2. When a tensor product state is an eigenstate of both Hamiltonian 1, H1 for particle state 1, and Hamiltonian H2 for particle state 2, then the separate energy eigenvalues add to give the total energy of the combined state. Because that tensor product state is an eigenstate of H1 tensor product I, tensor product 1, or I identity, and it is a eigenstate of identity tensor product H2. So it is an eigenstate of system Hamiltonian H. For two-particle spin states, the tensor operator S sub z to determine the z component of intrinsic spin angular momentum for the combined total state from the individual particle spin states is S sub z for the total tensor product state is defined as S sub z for particle 1 tensor product with identity for particle 2 plus identity for particle 1 tensor product with S sub z sub 2 for particle 2. And likewise for S sub x and S sub y, just carry through the x and y. When a tensor product spin state is an eigenstate of both SZ1 for particle 1 and SZ2 for particle 2, the separate intrinsic spin angular momentum z component eigenvalues add to give the total intrinsic spin angular momentum z component of the combined state. This is a possible time to take a break. Now, a little trickier is total angular momentum. Total spin angular momentum, S, with a vector arrow above it for two particles, is more complicated. It is conceived as a real space vector, so components x component, y component, and z component, Cartesian components, of three tensor operators. So S operator vector is defined as the x unit vector times the operator S sub x. This is a tensor operator, S sub x, the tensor operator that we had earlier. S sub x, tensor operator. So, tensor operator S vector is x unit vector times tensor operator Sx plus y unit vector times tensor operator Sy plus z unit vector times tensor operator S sub z. The operator S squared, the square of the magnitude of total spin angular momentum, is the dot product of S vector with itself, and it's an important operator. It's the dot product of S with itself, which means that it is, so it's the dot product of this with itself, which means we're going to get tensor operator Sx squared, tensor operator Sx times itself, which we will have to figure out, plus tensor operator Sy squared plus tensor operator Sc squared. But there's no longer any components here. The components are gone. So this is a tensor operator. We need to figure out what it is, but it is a plain old tensor operator, no arrow. We're going to need this in the next section, so we're going to continue. This might seem complicated, and if it is, skip it, move ahead. We need the result, you don't necessarily have to follow every step, but we're going to need the result in order to do to sum angular momenta. Sx squared is Sx, the operator Sx operating on the operator Sx. And we know what Sx is. Sx is a tensor operator. It is Sx1 tensor identity plus identity tensor Sx2. We need to take that operator and operate on another copy of itself. And operators are distributive. So we can multiply. This is two terms operating on two terms. So we're going to get four terms. We're going to get Sx1 tensor I operating on Sx1 tensor I, and that's going to be Sx1 squared tensor I. Identity operating on identity gives identity, so it's going to be this. If I've skipped some steps in explaining how operators work, I am sorry. Let's continue from here. So this term operating on this term is going to give Sx1 squared tensor I. Sx1 tensor I operating on this term is going to give Sx1 tensor Sx2, and that's also what we're going to get from this term, I tensor Sx2 operating on Sx1 tensor I. So we're going to get two copies of that. And then this term is going to operate on this last term, and we're going to get I tensor product Sx2 squared. Now, S squared is Sx squared plus Sy squared plus Se squared. We could write out Sy squared and we could write out Se squared, but it's going to be the same as this, just with Y instead of X or Z instead of X. And then when we add them all together, it's going to turn out that instead of Sx1 squared tensor product I, we're going to get Sx1 squared plus Sy1 squared plus Sz1 squared, parentheses, tensor product with I. And that is the same as S1 squared tensor product with I. And this term here, we're going to get identity tensor product with S2 squared. So S1 and S1 squared, those are operators only on the spin state of particle 1. S2 squared is an operator on the spin state of particle 2. However, we also are going to have these terms 2 times parentheses Sx1 tensor Sx2 plus Sy1 tensor Sy2 plus Sz1 tensor Sz2, and those don't magically go away. So we need to keep those. Now, this form is fine for our needs, but it's also sometimes written, often written, in this way. S squared is S sub 1 squared tensor product identity plus identity tensor product S2 squared plus 2 times the vector dot product of S1 vector with S2 vector. That gives this term in parentheses. We're probably not going to use that form, but you might as well see that form. It would be in any book you would look at. This is a possible time to take a break. Now, what we've done so far was not specific to spin 1/2, but now let's take both particles to be spin 1/2. We know the Pauli matrices for measuring spin in each direction, x, y, z, and we know that for each particle, the square of the magnitude of the spin angular momentum is 3/4 h bar squared. So for two spin 1/2 particles, S squared is going to be equal to 3/4 h bar squared identity tensor identity plus 3/4 h bar squared identity tensor identity plus 2 times 1/4 h bar squared, because each of the S terms will have an h bar over 2 and then a Pauli matrix, so we could take the h bar over 2 out here. And then there's going to be these products of Pauli matrices. Pauli matrix sigma x, tensor product sigma x. So this is sigma x operating on the first particle's spin state, tensor sigma x operating on the second particle's spin state, plus sigma y tensor sigma y plus sigma z tensor product sigma z. And we can do some simple math on that, arithmetic, and we get the following. S squared equals 1/2 h bar squared times a big parentheses, 3 times identity tensor identity, plus sigma x tensor sigma x, minus, now here I've changed it from sigma y. I've pulled out this I and this I so that I could turn it into minus and get rid of the imaginary number. So minus this real matrix tensor product with this real matrix plus sigma z tensor sigma z. That is S squared for two spin 1/2 particles, and we're going to need that in the next section, which is why we went through this much work. If you didn't follow every step, that's fine. If you don't like this result, that's fine too. It's going to lead to an even simpler result in the next section. This is a possible time to take a break. Addition of spin angular momentum. In quantum mechanics, as in classical mechanics, total angular momentum is conserved for a closed system, and the total angular momentum of the system is the sum of the angular momenta of the elements of the system. However, angular momentum in quantum mechanics is complicated because particles do not have definite position and momentum. Total angular momentum operators add, and any directional component, for example, the z component of total angular momentum, adds as an operator. Total angular momentum is characterized by two observable Hermitian operators: the z component of total angular momentum and the square of the magnitude of total angular momentum. Now we're only going to cover the angular momentum of two particles' spins, but a class or a book would also cover the addition of electron orbital angular momentum and spin angular momentum. Let particle 1 have spin S1. So it's a spin 1/2 particle or a spin 1 particle or whatever. And particle 2 have spin S2. It turns out that the eigenstates of total spin angular momentum squared for the pair of particles can have any of the following total spin values S, being one of the following. It can be S1 plus S2, S1 plus S2 minus 1, S1 plus S2 minus 2, continuing until we reach the absolute value of S1 minus S2. Any of those possible values, the combined state of those two particles can have as an eigenstate of total S squared. Now, for that value of S, the eigenstates of S squared, they're going to have eigenvalue S times S plus 1 h bar squared. We're not going to prove that. Now, if we want to replace S2 with the spatial orbital angular momentum quantum number L, we get possible eigenvalues of total angular momentum, orbital plus spin, but we're not going to do that in this lecture. Now, for the remainder of this lecture, we're going to restrict ourselves to 2 spin 1/2 particles. So S1 is going to be 1/2 and S2 is going to be 1/2. So we're no longer going to need to write S1 and S2. They're just going to always be 1/2. For 2 spin 1/2 particles, the eigenstates of total spin angular momentum squared, S squared, for the pair of particles can have total spin values S being 1 or 0. 1/2 plus 1/2 is 1, and we keep decrementing it until we reach absolute value of 1/2 minus 1/2, which is 0. There's only 2 values, 1 and 0. It turns out that simultaneous eigenstates of Sz, so simultaneous between Sz and S squared, can have eigenvalues of Sz being plus 1 h bar, 0 h bar, or minus 1 h bar for S equals 1, or 0 h bar for S equals 0. So a spin state may be an eigenstate of S squared and or Sz, or it might be a superposition state. This is a possible time to take a break. We want to find spin states of 2 spin 1/2 particles that are simultaneously eigenvectors of S squared and Sz. And there's a procedure we could use to find them, but really what we're going to do is we're going to just operate on our 4 prior pure basis states and the 4 prior entangled basis states, and we're going to see if any of them are eigenvectors of these tensor product operators. I'm going to give you the results here. I'm not going to show you how I got them. You can verify these values. It's not difficult, but you have to be careful not to make any mistakes. I encourage you to do that because it may be a little confusing about why aren't all of the 8 basis states that we talked about earlier, why aren't they all eigenvectors of S squared? Why aren't they all eigenvectors of Sz? And really the only way to know that is to actually take the operators that we previously wrote and operate on those states and see what you get for a result. And I'm not going to take up your time doing that all here with you, but I encourage you to do it yourself. So for 2 spin 1/2 particles, the first column is going to be the spin state, basis state. The second column is if the state is an eigenvector of S squared, what is the eigenvalue? And then the third column, if the state is an eigenvector of S sub z, what is the eigenvalue? The pure state up, it is an eigenvector of the tensor product operator S squared. The eigenvalue is 2h bar squared. You can verify this for yourself. I'm not going to do it in this lecture. For best understanding, you should verify each of these cells by yourself. It'll take you a while. You might spend a half hour on the whole exercise, but you will understand it better than just believing me. Now, tensor product state up is an eigenvector of S sub z, and its eigenvalue is plus 1 h bar. So great, we've already found a state that is an eigenvector of both, a simultaneous eigenvector of both operators, S squared and NSE. That's great. We're doing great. Now let's take pure state up down. If you operate on it with tensor operator S squared, you will get a result, and that result will not be a constant times up down. It will have other terms in it. So up down is not an eigenvector of S squared. It is an eigenvector of S sub z with eigenvalue 0h bar. Tensor product pure state down up is not an eigenvector of S squared. It is an eigenvector of Sz with eigenvalue 0h bar. Tensor product pure state down is an eigenvector of S squared with eigenvalue 2h bar squared, and it is an eigenvector of Sz with eigenvalue minus 1 h bar. So with our 4 pure state basis vectors, we found that 2 are simultaneous eigenvectors of S squared and Sc, and 2 are not. Now let's look at the 4 Bell state entangled states that we previously identified. It turns out that all 4 of them are eigenvectors of S squared. And their eigenvalues are 2h bar squared, 2h bar squared, 2h bar squared, and 0h bar squared for this Bell state, Bell basis state. But these first 2 are not eigenvectors of S sub z. The second 2 are eigenvectors of Sc with eigenvalues 0h bar. So we investigated 8 states, 8 tensor product states, and found that 4 of them are simultaneous eigenvectors of S squared and S sub z. This is a possible time to take a break. For 2 spin 1/2 particles, we found 4 spin states that are simultaneously eigenstates of S squared and Sc. 3 states have total spin of 1 because the eigenvalue for S squared was 2h bar squared, and we can rewrite 2 as 1 times 1 plus 1, so this is S times S plus 1. So the total state, total spin is 1 for these 3 states. These 3 spin 1 So we call them spin 1 states because S equals 1. For the individual particles, the spins are 1/2, but for the combined state, the tensor product state, these 3 states have total spin 1. These 3 are called the triplet state or the triplet states. There are 3 of them. Pure state up, which has eigenvalue plus 1 h-bar for SZ. Entangled state, 1 over square root of 2 up down plus down up. That has eigenvalue 0 h-bar for SZ. And pure state down, which has eigenvalue minus 1 h-bar for SZ. And there's a 4th state, 1 state, that has total spin of 0 because its eigenvalue for S squared was 0 h-bar squared. This spin 0 state is called the singlet state. There's only one of them, and so it's called the singlet state. And it is entangled state 1 over square root of 2 up down minus down up. And that has eigenvalue 0 h-bar for SZ. From here out, we're going to use these 4 spin states as our new orthonormal basis for describing the combined spin states of 2 spin 1/2 particles. You can verify that each of the 4 is normalized and that they're all orthogonal to one another. So 2 particles may be in one of these simultaneous eigenstates of S squared and SZ, or in some superposition state. If there is no external magnetic field, generally the triplet states will have the same energy as one another, and this will be different than the energy of the singlet state. Which state has the lower energy depends on the specific case, as we'll see in the remainder of this lecture. This is a possible time to take a break. Identical indistinguishable particles and the Pauli exclusion principle. Any 2 electrons in the universe are identical. Likewise, any 2 protons in the universe are identical. Any 2 neutrons in the universe are identical. In quantum mechanics, identical particles are indistinguishable. If the particles interact or if they're in near proximity, there are no classical particle trajectories by which we can forever keep precise track of each particle. We can't label. Mathematically, we can label one particle particle 1 and label one particle 2, but we can't put a magic marker on the electron and say, you're electron number 1, so when I see you later in the experiment, I'll know that you were electron number 1. Can't do it. There's no such magic marker for electrons and protons and neutrons. And it turns out this is really important. It's complicated. It is complicated. There's no doubt about it. Quantum mechanical states must account for this. It restricts how reality can be in the universe in kind of an amazing way. In this lecture, we have labeled one particle as particle 1 and the second particle as particle 2. If the 2 particles are identical, they must be indistinguishable in all measurements and observables. Quantum mechanics handles this by restricting allowed states based on exchanging the 2 labeled particles in the state. For any total system tensor product states, spatial wave functions plus spin states of two or more particles, if the two identical particles with mass, photons are a little funny, if the two identical particles with mass are exchanged, the total system state, spatial plus spin, must be unchanged if the two identical particles are bosons, they have integer spin. This total system state is symmetric or even parity with respect to exchange of the two identical bosons, or must be negated, it must change sign if the two identical particles are fermions, they have half odd integer spin, like electrons, protons, and neutrons. This total system state is antisymmetric or odd parity with respect to exchange of the two identical fermions. At this point, this will all seem very confusing, but bear with me. Consider a system that includes two identical indistinguishable fermions. If the two fermions are individually in different spatial states, different orbitals for electrons, we can elect or choose to re-express the spatial state as one linear combination, superposition, spatial state that is symmetric with respect to exchange of the two identical fermions. Or alternatively, we can compose a second linear combination that is antisymmetric with respect to exchange of the two identical fermions. Therefore, it's allowable for this total system to have a total spin state that is either antisymmetric or symmetric with respect to exchange of the two identical fermions, because they were in different spatial states, different orbitals. This is a possible time to take a break. Now consider a system that includes two identical indistinguishable fermions where the two identical fermions are in the same spatial state. For example, two electrons in the same orbital. Exchanging those two identical fermions, it can't change the spatial wave function because they were both in the same wave function. So in order for the total system state to be antisymmetric with respect to exchange of the two identical fermions, the spin state must be antisymmetric with respect to exchange of the two identical fermions because they were in the same spatial state. For two spin 1/2 particles, the only combined state that is antisymmetric with respect to exchange of the two particles is the singlet state, which you can verify. Let's take a quick look at that. Here we have the singlet state. Up, down, minus, down, up. If we reverse the two particles so that this becomes down, up, and this becomes up, down, well, that gives an overall minus relative to the initial state. So it is antisymmetric or odd for exchange. But let's look at these three triplet states. If we have the state up, up, and we reverse them, we still have the state up, up. So it is symmetric or even with respect to exchange. How about up, down, plus down, up? Well, if we reverse them, we end up with down, up, plus up, down, but that's the same as we had. I mean, the two terms exchanged, but they were being added together, and the result does not change. If we have down, down, and we exchange the two, we still have down, down. So the three triplet states are symmetric or even for exchange, and the singlet state is antisymmetric or odd for exchange. So, for two identical, indistinguishable spin 1/2 particles, such as electrons, in the same spatial state, for example, the same orbital for the two electrons, their combined spin state can only be the singlet spin state, which is the spin 0 entangled spin state. That's the only possibility. It turns out that three or more identical fermions cannot occupy the same spatial state or orbital. The only spin state that is antisymmetric for all exchanges of pairs of three particles or more is the 0 state, and we're never interested in the 0 state. There's no particles in the 0 state. This brings us to Wolfgang Pauli's exclusion principle. Two or more fermions, for example electrons, in a system cannot be found in the same total state, spatial plus spin. This is proven in the final chapter of MITx course 806X, the third course in their undergraduate series on non-relativistic quantum mechanics. So it takes 3 semesters of hard work for an MIT junior to get this far in physics. In chemistry, we're given without proof the Pauli exclusion principle immediately after learning about atomic orbitals as a college freshman or sophomore or even in high school. In a chemistry course, you might hear the Pauli exclusion principle expressed differently. At most, 2 electrons can occupy a single atomic orbital. Expressed this way, it's implicit and unstated that there are 2 spin states for the spin 1/2 electrons for each atomic orbital spatial wave function. So 1 electron per total wave function, spatial plus spin state. When 2 electrons occupy a single atomic orbital, they must have opposite spin. You've undoubtedly learned this, heard this, read this. But now we know that actually the spin state must be the special entangled singlet spin state, which is antisymmetric for exchange of the particles, which allows the pair of electrons to occupy the same spatial wave function. The singlet state has 0 total spin, so the pair of electrons does not contribute spin angular momentum or spin magnetic dipole moment to the atom or molecule. This is a possible time to take a break. 2 electrons in the same orbital. An atomic or molecular spatial orbital can be occupied by at most 2 electrons, per Pauli's exclusion principle in the previous section. When the orbital is occupied by 2 electrons, The electrons are identical and indistinguishable and must be in the singlet spin state, which is the maximally entangled spin state with total spin 0. The pair of electrons contributes 0 spin angular momentum to the atom or molecule. Books usually show the electrons as having opposite spins, one up, one down. This is graphically simple and memorable, but only partly correct. The electrons are in the singlet spin state, not in the triplet spin state, ket plus. That the two electrons have opposite spins does not magically eliminate their electrostatic repulsion for one another. The Hamiltonian for their spatial state must include their mutual electrostatic repulsion, though this then requires numerical solution, not analytical solution. Almost all of the electrons in your body are paired up, pairs in orbitals. They're paired up in quantum entangled singlet spin states. Your electrons are entangled. You may have heard of this word entangled in articles about quantum mechanics, and it sounds very exotic. Almost all your electrons are entangled. This is the same quantum condition as the quantum entanglement of modern quantum technologies. Quantum computing, quantum communication, quantum teleportation. However, in those modern quantum technologies, the two entangled particles of interest are not bound together spatially, whereas the entangled electrons in your body are paired in bound orbitals. In the next lecture, D6, we will talk about pairs of quantum entangled particles that are not bound together spatially. If our universe had electrons that were bosons, spin 0 or spin 1, instead of spin 1/2 fermions, then atomic and molecular orbitals could be occupied by any number of electrons. The Pauli exclusion principle would not apply for bosons. It would seem that all electrons in an atom could then occupy the ground state orbital, and there would be no such thing as filled shells or valence for atoms. We probably could not have the covalent bonding and bond angles that chemistry has in our universe. But we don't have that. Electrons in our universe are spin 1/2 fermions. This is a possible time to take a break. The oxygen molecule, triplet oxygen. A molecule of oxygen, O2, has two electrons that are unpaired in two different molecular orbitals, antibonding, pi x antibonding and pi y antibonding. All the other electrons, they're paired in orbitals, and they're not of interest to us here because they're paired, they're in singlet spin states, they contribute spin 0, but two electrons in the ground state of O2 are unpaired, and that's important. It's different than most diatomic molecules, different than nitrogen and fluorine and chlorine. In those diatomic molecules, all their electrons are paired. Not so in molecular oxygen. Since these two indistinguishable electrons in molecular oxygen are in different spatial orbitals, their combined spin state is allowed to be either the triplet spin state, spin 1, or the singlet spin state, spin 0. These two spin states have different energies. One of them will be the ground spin state. Hund's rules, whose quantum mechanical underpinnings I only partly understand, say that these two electrons in different half-filled orbitals will have their spins parallel in the ground state. And so that will be a spin triplet state, spin 1. This ground state is called triplet oxygen. As far as I can tell, these molecules should split into 3 beams in a Stern-Gerlach experiment, but I don't know whether that's ever been demonstrated. Now, the first excited state is a singlet spin state, and it's about almost 1 electron volt higher in energy than the ground state triplet spin state. And that 1 electron volt, that is a near-infrared energy. The electronic energy of the excited state is higher than the ground state by quite a bit, because the 2 electrons have higher probability to be in closer proximity in the singlet spin state than in the triplet spin state, so the energy of their electrostatic repulsion is increased. 2 electrons avoid being too close to one another when they're in the triplet spin state, which lowers the triplet state energy relative to the energy of the singlet spin state, where the 2 electrons are more likely to be close to one another. At room temperature, oxygen molecules in the gas state are nearly all in the ground state, in the triplet state. The first excited state is forbidden from decaying to the ground state by an electric dipole process, which gives it a medium-long lifetime. Its lifetime is as high as 72 minutes, so any molecule in the first excited state could take minutes or hours to decay to the ground state. Triplet oxygen is paramagnetic, attracted to a magnet, due to the 2 unpaired electrons' parallel magnetic dipole moments due to them having parallel spins. This attribute can be used to build an instrument to measure oxygen content in air. Also, a magnet can pick up liquid oxygen. It's attracted to the gap between magnets' poles. The ferromagnetism of iron and nickel is also due to unpaired electrons with parallel spins, but they are more complicated and we will not cover them. This is a possible time to take a break. Electron and proton spins in hydrogen atoms. Hyperfine splitting. For a hydrogen atom, not deuterium, the spins of the proton and electron can be in either the singlet spin state or the triplet spin state, or any superposition. Because the 2 particles are different, they are distinguishable. It turns out that in the atom's ground electronic state, the 1s orbital, the singlet spin state, spin 0, energy is lower than the triplet spin state, spin 1 energy, by about 6 millionths of an electron volt. 5.87433 by 10 to the minus 6 electron volts. And that energy corresponds to a microwave photon frequency. And it happens that it has an extremely precise frequency. 1.42040575176667 gigahertz, and an extremely precise wavelength, 21.1061140542 centimeters in vacuum. These two energy levels with this energy gap are called the hyperfine levels for the hydrogen ground state. Transition between these two levels is called a spin-flip transition, and it is important in the radio astronomy of our galaxy and other nearby galaxies. The microwave frequency and wavelength are called the hydrogen line, the 21 centimeter line, or the H1 line. For a hydrogen atom, the ground state electronic state is the 1s orbital, which is spherically symmetrical. The expected value of position for the electron corresponds with the proton, or the nucleus. This is also the most probable location in space for the electron. The proton and electron act as magnetic dipoles. Each exerts a magnetic force on the other. With their spins antiparallel in the ground state singlet spin state, their magnetic dipole moments are parallel because the electron has negative charge, and the magnetic dipoles attract one another in this configuration. This would be the lower energy configuration for two current loops with the same axis and direction in space, or if the aligned magnetic dipole moments share the same axis, so the north pole of one was close to the south pole of the other on the same axis. For the triplet spin state, the two magnetic dipole moments are antiparallel and repel one another in this configuration, increasing the energy. The transition from the excited triplet spin state to the ground state singlet spin state is extremely forbidden. Its mean lifetime is 10 million years. This extremely long time constant means that the natural line width of the emission line is extremely narrow and sharp, which is why it has such a precise value of wavelength and frequency. This sharp line width means that radio astronomy on Earth can detect and determine different Doppler shift velocities and temperatures of the emitting hydrogen atoms from different locations between stars in our galaxy. Radio astronomers use this to determine the rotation curve of the Milky Way and other nearby galaxies, and to determine the distance to different points in our galaxy, to estimate the mass of some galaxies, to estimate the temperature of different hydrogen clouds in our galaxy, and to get information about the time when the first stars or quasars in our universe began to shine, emit ultraviolet light, and ionize, called re-ionize, the neutral hydrogen atoms in and surrounding those galaxies. This hydrogen line was used in 1952 to tell astronomers that our Milky Way galaxy has a spiral structure, which you cannot see with visible light astronomy. It's amazing that we can detect the signals emitted by hydrogen atoms after a million years after they've been excited. We can detect them, atoms in the high vacuum of the interstellar medium. But the volume of space is huge, the number of atoms is huge despite their low density, their vacuum, almost vacuum. And the emission is detectable on Earth. It's not blocked by our atmosphere, and it's not blocked by interstellar cosmic dust. So we can see through interstellar dust clouds. For example, we can see to the center of our galaxy, whose visible light is blocked by dust. This is a possible time to take a break. Proton spins and hydrogen molecules. In the hydrogen molecule, H2, not deuterium, hydrogen molecule electronic ground state. The two identical indistinguishable electrons, they're bound in the same molecular orbital, a sigma bond, in the spin singlet state, spin 0, and so they're not of much interest. Their spin is not of much interest because it cancels the spin 0. The two protons, they're identical indistinguishable fermions. They're separated. They're nuclei of two different atoms in the molecule. They're separated but identical particles. We can choose to express the spatial wave function for the two protons' spatial state as a superposition that is either symmetric or antisymmetric with respect to exchange of the two identical fermions. Therefore, it is allowable for this total system to have a total spin state for the protons that is either antisymmetric or symmetric with respect to exchange of the two identical fermions. It turns out that the proton singlet spin state, spin 0, which is called parahydrogen, that its energy level is lower than the proton triplet spin state, spin 1, called orthohydrogen. I was unable to find a reference to the energy difference due to spin alone, but I estimated it to be around 10 to the minus 9 electron volts. This energy difference is so small that rotation of the hydrogen molecule about its center of mass contributes more energy than this and contributes rotational angular momentum. At low temperatures, the energy level difference between parahydrogen and orthohydrogen, including molecular rotation, seems to be around 1/100th of an electron volt. A gas of hydrogen molecules is a temperature-dependent mixture of orthohydrogen and parahydrogen. The energy difference has implications for the process of liquefaction of hydrogen and its storage. When it's liquefied, it's important to cool it so that all of the molecules are in the lowest energy state. So you have to remove that heat. Let's ignore molecular rotation, though we really should not, and just think about the two protons. The protons are indistinguishable fermions and are not located at the same point in space. The protons act as magnetic dipoles. Each exerts a magnetic force on the other. With their spins antiparallel in the singlet spin state, their magnetic dipole moments are antiparallel. This would be the lower energy configuration for two current loops at separate locations in one plane. For the triplet spin state, the two magnetic dipole moments are parallel, increasing the energy. However, molecular rotation dominates the energy difference, so it's more complicated than we will cover. An odd fact, two hydrogen atoms unbound in space or in our atmosphere, if they approach one another, they want to bond, but generally they cannot get rid of their excess energy and angular momentum to bond to form a molecule unless they're in contact with some surface, such as a dust grain. This is a possible time to take a break. Proton and neutron spins in the deuterium nucleus. The deuterium nucleus, which is called a deuteron, contains one proton and one neutron. Since the two particles are different and distinguishable, we would expect that the spins of the proton and neutron could be in either the singlet spin state or the triplet spin state, or any superposition. It turns out that the deuteron's nuclear triplet spin state, spin 1, is lower in energy than the nuclear singlet spin state, spin 0, by about 2.3 million electron volts. Pretty large number. However, Wikipedia says that the singlet spin state is just barely unbound. The neutron will separate from the proton and leave the nucleus. Since the proton and neutron are composite particles, 3 quarks each, their behavior in intimate proximity is different from point-like particles. The proton and neutron are adjacent, but not located at the same point in space. The proton and neutron act as magnetic dipoles. Each exerts a magnetic force on the other. With their spins parallel in the triplet spin state, their magnetic dipole moments are antiparallel because the neutron has a negative G factor. This would be the lower energy configuration for two current loops at separate locations in one plane. This is a possible time to take a break. Let's recap a little. Two electrons in the same atomic orbital or molecular orbital can only be in the singlet spin state, spin 0, which gives a total wave function that is antisymmetric for exchange of the indistinguishable electrons, which are fermions. The following case had lower energy for the singlet spin state, spin 0, than for the triplet spin state. The spins of the proton and electron in a hydrogen atom. The particle locations coincide, and their magnetic dipole moments are parallel when their spins are antiparallel. The energy difference is about 6 millionths of an electron volt, which is a microwave photon frequency of 1.4 gigahertz and a wavelength of about 21 centimeters in vacuum in free space. The mean lifetime of the excited state is 10 million years. The following cases had lower energy for the triplet spin state than for the singlet spin state. the two unpaired electrons in a molecule of oxygen, O2, triplet oxygen, which is paramagnetic. The energy difference is about 1 electron volts, and this is due to differences in electron positions and repulsion between the two states. That 1 electron volt is a near-infrared energy. The lifetime of the excited state is as high as 72 minutes. The proton and neutron of the deuterium nucleus. The energy difference is about 2.3 million electron volts. But the singlet state is unbound. Molecular hydrogen is more complicated because the energy of rotation of the molecule about its center of mass dominates the energy difference between the proton spin states. A gas of hydrogen molecules is a temperature-dependent mixture of orthohydrogen and parahydrogen. This is a possible time to take a break. NMR and MRI, magnetic resonance imaging, MRI, uses the nuclear magnetic resonance, NMR, spin manipulation of the proton of the hydrogen atom. A strong external magnetic field aligns all the unpaired magnetic dipoles in the portion of the body being imaged. A smaller time-varying magnetic field perturbs the spins of unpaired protons, which emits a radio signal that the machine detects. The emitted frequency depends on the chemical environment of the hydrogen atom, to what atom it is bonded, with what bond length, and what other atoms are nearby. The MRI machine detects where each signal originates and its timing and uses these to distinguish and image different tissues. In the next lecture, we will cover entangled states between separated particles. All the entangled states in this lecture were between particles that are bound together. This is the end of lecture D5.